So I hope the exam went all right for you. We're going to be moving on to the next part of the course now, which is slightly more abstract in the beginning. We're going to develop a set of tools that revolve around working with expressions and functions with multiple definitions based on what we've learned about how to manipulate expressions. And then with that, we're going to actually start working on applications. So we'll see applications in various areas of mathematics, linear algebra, calculus, basic differential equations that can create a groundwork going forward from this class for mathematics in a wide range of applications. So today we're going to talk about how to work with expressions in terms of substitution and in pattern matching. And pattern matching in particular is kind of an abstract thing, but also one of the most powerful things that you can do with any programming language, and Mathematica specifically. So let's start by talking about rules. And we've already seen rules in a previous homework exercise when we generated a list of rules. And if you think about what a rule was in that context, it's a way of assigning a replacement for a symbol or an expression. So the rule I've built here, rule x2, is a rule that looks for copies of x and says everywhere you see an x, you should be able to convert that into a 2. So rules don't actually mean anything unless they're applied to an expression, whether that be an x or an expression that contains lots of x's inside of it. The rules themselves are actions that need to be performed or applied. And we apply rules with the replace function we'll talk about in a second. So there's two different ways that you can create rules. You can create rules using the rule command itself. So everywhere that you see everywhere that you see a capital R, replace that capital R with a 32 would give you a rule that says everywhere you see an R, replace it with a 32. Okay. And there's a shorthand notation for creating these where you can actually just write the arrow itself. So if you wrote this down, R turns into 32, that's the shorthand notation for rule. So rules got a shorthand with the arrow. So rules are applied to expressions using the replace command. And the shorthand for that is this /dot right here. So if I took the expression x squared plus 3, and then I replace inside that expression with some rule, what the replace command does is it goes inside whatever you fed into it, and it looks for every instance it can find of the expression you're trying to replace, in this case an x, and it replaces it with what you've said to replace it with. And then if it can, it evaluates that expression. So what we get when we replace x with 2 in the expression x squared plus 3 is 2 squared plus 3, which is 7. And you can see here that you get the same output if you use the shorthand notation for this as well. To give you an idea of another rule that we might use, you could do something like x squared plus 3, but now let's suppose that we're going to replace x with some complicated thing like ABC. And you can see that what happens here is the x gets replaced, the ABC slots in, and then to the extent that it can, Mathematica evaluates that expression. So we haven't done much yet with the solve command. When you solve an equation with Mathematica, it doesn't produce a number. It produces a rule that says whatever the variable that you solve for can be replaced with some complicated or simple expression. And so if we solve the cubic equation, x to the third minus 2x plus 1 is equal to 0, what we get is a set of replacements. We get rules that say x could be replaced with 1, x could be replaced with 1/2 times minus 1 minus square root of 5, and so on. If I actually want to convert that into a list of numbers, a very simple trick for doing that is actually just to replace the variable x with the output of that expression. So as another example here, we could do something like if I asked it to find x to the third minus 1 is 0, we get these three expressions. You notice two of these are complex numbers. This actually came up on the quiz last week. When you take fractional exponents of negative numbers, Mathematica interprets that as what's called a root of unity, which is a complex number that when you cube it, you end up with 1. But it's a very useful concept. It comes up in every application where complex numbers are used. And again, if I want to see what those numbers are specifically, and not as rules, but as actual numbers that I could call from the list, a very typical trick is to say, take the x that we solved for, and then just do the replacement. And what's happening here is x in each one of these expressions here each one of these rules is being applied to the x. And so since we had 3 rules, we end up with 3 replacements. There are some restrictions to keep in mind about the way that the replace command works. /dot is shorthand for the command replace all, and replace all treats all expressions that you've replaced as equal in importance, and it sort of walks through the original expression left to right one time and looks for every place where it sees a substitution that needs to be made. So that could have an effect on what you're trying to do if you have multiple replacements, but they involve the same variables. So as an example here, if we took the expression x plus 2y and we asked Mathematica to replace every time we see an x, put a y in there, and every time you see a y in there, put an a in its place, it's not going to replace everything down to the a's. If we actually evaluate this, you see that what we get is 2a plus y. And the reason is, as Mathematica has walked down this expression left to right, it saw the x and did that replacement, and then it moved on. Then it saw the y and replaced that with a. So it did not pick up the original y that you introduced. So if you want Mathematica to act recursively, that is, to simplify until it can't simplify any further, then you don't use replace all, you use a command called replace repeated. And what that will do is it will walk down the expression, and then we'll go back to the beginning and try to apply the replacements again. So if we use that command, which has shorthand //dot instead, and we apply it to the same input we had before, now we get 3a, because what's going to happen now is the intermediate step, which was 2a plus y, now Mathematica goes back through again and applies the same rules and says, well, there's still a y in here, so I'll replace that with an a, and then evaluates to 3a. Now, anytime you're doing an iterative process, you can create conditions on which that process will never finish. And in replacement rules, that's really easy to do if you create replacements that bounce back and forth. So what do I mean by that? Well, here's a setup where we have started with the expression x plus 2y, and we told Mathematica repeatedly replace x's with y's, and repeatedly replace y's with x's. And so if you run this, there's no exit condition because all of the x's and y's will switch places, but then you've told Mathematica to keep going, and so it goes back through and switches them back and forth. And if we actually run this command, we can see that it actually runs through 65,000 times before it quits. Okay. This is still something that you want to be able to do, and the way that you can control how many times the replace command acts, if you're trying to create, say, a nested function or use this in place of a composition, you can use the option max iterations, which controls how often Mathematica will run that replacement cycle. So if we look for max iterations of this expression 1, then one time through, Mathematica replaces an x with a 1 over 1 plus x. This is a structure called a repeated fraction. If I do it twice, I get 2 repetitions of putting that thing inside of itself, and so on. If you don't want it to throw this this error command here, where'd my cursor go? If you don't want it to throw this error command every single time that you're running a replace all loop like this, or any command where you want it to be quiet, you can actually just tell it, be quiet. In which case it will just hide whatever error messages there are. Now you should be careful with that because sometimes you want to see what the error messages are. So you only use quiet if you absolutely need to, is a good rule of thumb for this. A very powerful thing about rule replacements is that they work on expressions. They don't just work on concrete exact matches. So the rules we had up here, we have x is mapped to y and y is mapped to x. Those are very concrete replacements. But maybe what we want is to replace anything in a particular slot in an expression with something else. So one example that's good for this is something like, let's create all these permutations, right? Just so we have a list of objects we can work with, and all of the entries are going to be different. So the permutations command gives you every possible arrangement of the objects that you feed it. And so what we're looking at here is every possible ordering of x, y, and z. Now, what does this replacement command here do? What it looks at this list, and it looks at individual entries in this list, like this one. Let's just take a look and see what this is actually doing. If we took that expression, which is a list with X, Y, and Z hidden inside of it. And we told it that what we wanted to do was replace A, B, and C, that is arbitrary expressions A, B, and C in the correct slots. And we want to replace that, say, with A plus B plus C. Then what it's going to do is look inside this little list, and it's going to look for the variables or whatever expressions that are in those slots, and then it's going to apply the replacement rule regardless of what the names of the things in those spots are. So you can think of this as representing not a variable to replace, but an expression in a particular location to replace. And that's a very powerful thing to be able to take lists and construct them into more complicated objects. So this command at the bottom here, what we're really doing with this is we're taking the permutations and we're replacing each entry in the list, which is a list itself of 3 objects, and it says look at each entry and take the 3 objects inside that list and convert them into A to the B to the C. And that's what the output is right here. Now this would work just as well. You can actually see what the difference will be. Maybe I'll just write a word in here, ball. And you can see what's actually happening is it doesn't care what the expression is inside there. You want to feed it a number, it is happy to do that too. Okay. The idea is that these expressions are agnostic about the structure of what is in those places. It just looks for what is in the slot of that particular 3-slot list. So what we've done here with the sort of structure and these expressions is a very basic form of what's called pattern matching. That is, we've built an object that structurally is what we want to work with. A list with 3 slots and 3 arbitrary expressions in the first, second, and third place, and then a rule that acts to combine those expressions in a new way. So the idea of structurally matching objects to each other, especially as a selection process, is the basis for pattern matching, and that's the next thing that we're going to talk about. So pattern matching is actually enormously powerful, but a little bit abstract, which means it can be hard to wrap your mind around how this works when you see it for the first time. So you can think about any object in Mathematica, and really any programming language, as being imbued with a set of characteristics. So the number 2, for example, has the property that it is even, and it has the property that it is an integer, and it has the property that it is a positive integer or a whole number, right? Just speaking mathematically now, not from a Mathematica perspective, but from a mathematical perspective. 2 is even, it's an integer, it's a positive integer, it's also a rational number because 2 is 2 over 1, it's a real number. There's a lot of characteristics that 2 carries as a mathematical object. In Mathematica, those characteristics are more restricted because we're thinking about them as a set of characteristics we can use to construct computer programs that make decisions about the objects that we're working with. So let's take a look at, just at the beginning here, the example of x to the second. And we're going to use that as the basis for looking at what are the characteristics that Mathematica can look at, and how can we match like generic expressions to an object like x squared. So if we look at the full form of x squared, we see it's a power type object. That is, the head of the list is power and involves 2 sub-objects. There's an x and a 2, and the 2 is the exponent and the x is the base. So we can check if 2 expressions match in Mathematica by using the command matchq. It shouldn't be shocking that the expression, now notice this is not equality. We're not looking for equality. We're asking Mathematica, do the properties of these 2 expressions match each other? Do the patterns match? So it shouldn't be a surprise that x squared is a match for x squared as a expression. So if I want to be more generic, and if you've ever wondered why we're always putting that underscore after the variables when we define functions, what the underscore means is something. The underscore is a notation that means an expression of some unknown type. It's what's called a wildcard. It stands for lots of things. So when we write a with an underscore after it, when we're doing function definition, what we're really saying is, I want a generic expression, but for the purposes of what I'm going to be doing in my function, I want it to be called a. So with that underscore character, we can ask questions about patterns. So this question right here is the most generic question that we could ask matchq. Is x squared an expression? The answer is obviously yes, it is an expression. is x squared of the form x to the something. So you can see this is the pattern we're trying to match. Is x squared an expression of the form x to the something? So remember, that underscore character is the something character, the wildcard. Is the head of x squared, the head, power? Match q x squared, and putting this in the second slot says, is x squared an expression of the type power? And the answer is yes. Is x squared of the type plus? No. Okay. So the real power of pattern matching is that we can combine these ideas together, and we can actually impose Boolean conditions on those as well. So more refined version of this might say something like, is x squared x to an integer? Remember, the underscore means something, but when we put a head after the underscore, we're asking, is the object in that place of a particular type? Is x squared of the form x to an integer? And the answer is true. Is x squared of the form x to a real number? And here you can see that Mathematica thinks of integers as a different category of object than the real numbers. Okay? It treats them different internally. It uses different algorithms to work with them. The reason that you might, if you need a reason for why it does that, if Mathematica thinks it's working with integers, it will only produce solutions to questions that involve those integers. It won't try to approximate them with decimal numbers. Okay, so x squared is not of the form x to a real number. We can go one step further with this and involve conditions. Now this mysterious looking expression right here says, is 5, in fact, we can just write down what it means, is 5 an integer, and also does it satisfy the condition that it is greater than 3? And so the question that this is answering is 5 an integer greater than 3? Okay, so here is where things start to look a little bit more abstract, but this is also where the power is in pattern matching. The fact that I can combine structural things. Is 5 an integer, but then with Boolean conditions that let me restrict things like domains. Is it an integer that is also subject to the condition that it is greater than 3? Is x squared of the form something to the something, but the something is even? Of course, that's true. Is x squared of the form something to the odd? False. Okay. To illustrate sort of this basic pattern matching, I want to look at problem 9.1. And problem 9.1 is concerned with finding out if a number is square free, which means that, so a number is called square free if none of its factors appears more than once, or has multiplicity bigger than 1. So this number, 234090, is not square free because it has 3 to the 4th living inside of it, and it also has 17 squared living inside of it. So what we want to be able to do is produce a pattern matcher that can look at the output of factor integer and recognize if anything other than a 1 appears in that second slot. Because if it does, then the number is not square free. So we want to be able to see that. Now the pattern here, again, these patterns start to look a little mysterious, but they're not that bad if you take a minute to actually parse them. What this pattern says is it the case that the list 3, 4 is a list of 2 entries? We know that it's asking to see if it's a list of 2 entries because I see the braces on the outside. I see an expression in the first slot and an expression in the second slot, but subject to the condition that whatever's in the second slot is bigger than 1. And if we run this command, we get true because 3, 4 is a list of 2 objects, and the second object is a 4, which is bigger than 1. Now, we can use matching or pattern matching to create sublists that meet a condition exactly the same way that we use the select command on the basis of a Boolean check for, say, equality or greater than or less than. We can do the same exact thing with pattern matching, except we don't use select. We use a command called cases instead. But structurally, they are parallel. Select uses a Boolean condition to select a sublist from some big list, and cases use a pattern match to pull a sublist from a big list. So if I apply to this list right here, so that is a list that has 4 lists of size 2 inside of it, and I'm asking Mathematica, from that list, find all of the expressions inside that have the form, they are a list of length 2, and the second list has a second entry that is larger than 1. And you can see that it pulled out the 3, 4, and the 17, 2, which is exactly what it was supposed to do. Okay. Now, is it the case that that list was empty? And the answer is no. It's not empty because it produced something. And this right here is something that we can use to ask if a number is square free or not. So here's what the build-up process would look like. The first thing we need to do is figure out how to produce that list of numbers. And how do we do that? We did that with the command factor integer. So we factor integer the number, what was the number we started with here? 234090. And we got that output. So the first thing we'll make this function do, maybe we'll make it square free q n. We'll just make it factor the number. Okay. With a delay. Okay. So the next thing we need to do with our function is we need to make it, so what's going to come out of that is going to be this type of list right here. And to that list, I want to apply this pattern match, and I want to select all of the things that had square or higher. So I'm going to take my pattern match that I built, and I'm going to drop this inside of the cases function. And let's try it. Let's just evaluate it on something. 234090. So right now, it produces a list of numbers that have square or higher multiplicity, right? So I know that 234090 has a 3 to the 4th power and a 17 to the 2nd power inside of it. I can use the trick that I'm going to set this equal to the empty set. And now if I evaluate, I'm going to get false. Why? Because the size of the list that came out of the cases command was not nothing. So let's pick a number that is square free and check it. But if I try square free of, so 2 times 3 times 5 is 30. Oh, good. 2 times 3 times 5 is square free because all of those numbers appear to the 1st power, but not the 2nd or higher. So in the same way that when we're working with select, oftentimes we only need select to produce one object. We don't need it to produce a whole list of things, especially if we're trying to compare something to an empty set, and we really just need one example. From an efficiency standpoint, I might just want cases to pick out one entry. And so cases is a little bit more specific than select in terms of how to specify that you want one entry. Because the first thing that happens is you have to tell it at what level should I look. So I want to look at level 1. And then I want to just stop if it finds one output. And you can see that it did that correctly by taking out the empty set. You can see that now we have it cut down so that no matter how many squares it finds, it's only going to produce one entry on the list. I can still set that equal to the empty set, and we retain the ability to see that a number is square free or not. So just for the standpoint of efficiency, when you're actually working with these things, when you're working on real mathematical problems and the outputs can be complicated, oftentimes restricting your selection functions down so they just produce a single example, if that's all it takes to fail, is good practice. So the last thing, and I think the best thing about pattern matching, is how we can use the ideas of pattern matching to look at multiple expressions. Up to this point, everything that we've looked at has just been single expressions or lists of single expressions. So it would be really awesome if we could use this to look at sequences of data. That is, whole lists of things where I can specify that I want to look for lists of a specific structure. And so in order to do that, we're going to introduce different versions of the wildcard character. So the first thing to remember is that match Q, if I feed it just a single underscore, looks for a single expression. So this evaluates as true because match Q says, here's a list with one object in it. Is that a list with one arbitrary expression inside? And the answer is yes. But if you ask it to evaluate a list with two things inside, Mathematica says, well, you're asking me if this list with two objects inside is a list with one arbitrary object inside. And the answer is no, that's false. Okay. If you want it's a little brain-bending subtlety here, what if you ask it this? Well, now the answer is true because Mathematica looks inside here and sees one object, which is itself a list that has multiple objects inside. So be careful with that. The main point here was, again, that we don't have a way of handling multiple expressions inside of a list. So single underscores represent single expressions. Double underscores represent non-empty sequences of expressions. So if I ask match Q, do you match x squared x to the third as a list with a sequence of objects inside that is not empty, then the answer is true. However, if I asked it, is this true? The answer is false, because what Mathematica is looking for is any number of objects inside that list as a sequence unless it's empty. If you want to allow the possibility of an empty list that is some completely like arbitrary, something could be there, something not could be there, you can use triple underscores. Okay, so is the empty set a set with something inside of it? No. Is the empty set a set with a sequence of things inside of it that are not empty? No. Is the empty set braces with any number of things inside of it, including none? Yes. So you might not see why we would need a pattern match that was empty or not empty until you start looking at how you can use this stuff to pull apart sequences of numbers instead. So I'm going to show you an example here where we're going to look at all of the permutations of 1, 2, 3, and 4. And then suppose I want to know all of the outcomes where 2 occurs before 3. Not right next to it, anywhere in front of it. So to do that, I'm going to use this command right here, right? And so let's see if we can understand what exactly this pattern match is doing. This will evaluate as true if it looks at a sequence over here in the left slot and it finds something or nothing, and then a 2, and then something or nothing, and then a 3, and then something or nothing. And the reason that we need to use the something or nothing is because if I used 2 underscores right here, I would be telling Mathematica 2 cannot occur at the front of the list because nothing empty can come first. Sometimes that's something you want to be able to do. In this case, what we're saying is, I don't really care what's in front of the 2, between the 2 and 3, or after the 3, as long as the 2 comes before the 3 in the list. And that's why this evaluates as true. In fact, this also evaluates as true. Okay. But this evaluates as false, because in that one, 3 came before 2. So if we apply this pattern match using cases to our list of permutations, you can see that precisely what we get out the other side is what we were after. In every one of these permutations, 2 occurs before 3, and it doesn't matter where in the list the 2 and the 3 occur, and it doesn't matter if there's things in between them or not. If instead I had required that something be between the 2 and the 3, you can see we get a different list. This is an output that has all of the permutations of 1, 2, and 3, where 2 is in front of 3, and also something is between the 2 and the 3. It could be one thing, it could be 2 things, but something has to be in the middle. Okay. So this sort of idea of sequence matching is extremely useful when you have lists of data that you're trying to detect patterns inside and select those that show certain structures. Okay, so pattern matching is very, very useful for working with lists or sequences. So let's look at problem 9.2. And what problem 9.2 specifically says is It wants us to identify which of the first 50,000 prime numbers have the number 2009 living inside them as a sequence. So, for example, the number 420097 has a 2009 living inside of it. So the first thing I want to do to solve this problem is find a pattern. But I'm not going to be able to find a pattern if I'm working with the number itself, because a number is not a sequence or a list that I can manipulate or explore. So the very first thing I'm going to do is I'm going to try to break this into a list of digits. And then from that list of digits, I can look specifically for that sublist that I'm after. So the very first thing I'm going to need to do is I'm going to need to do the integer digits. Okay, so now I've got a list of digits I can work with. Now, what pattern am I looking for? I'm hoping that if I run match q on this, remember, what I'm working with here specifically is this list of the digits. I would like to be able to see that 2009 occur right next to each other, but I don't care if they occur at the beginning of the number or the middle of the number or the end of the number. And so the specific pattern I'm going to use here is I want the list that came out of integer digits to have the form, I don't care what comes first, then it better have a 2, a 0, a 0, and a 9, and then I don't really care what comes afterwards. Does that match? Okay, good. Now let's verify that if I put a number in that does not have a 2009 inside of it, that I get a false out of this thing. So what if I put an 8 here? Okay, that's good. I get false because that does not have the sequence 2009 inside. Let's check and make sure that if the 2009 were split up, that I get a false. Good, that's also false. That's the reason why we put nothing in between these numbers. Specifying 2009 in order like that is a specific sequence that I'm saying has to occur in that order in that precise way. Okay, so let's fix that. So now I just need to figure out how to apply this in a cases command. And one way of doing that would be to map the integer digits command onto a list of the primes. So I guess the first thing we could do would be to create the range of numbers that we wanted. And then I guess I could map the primes onto that. Okay, that looks like a list of all these primes, starting at 2, 3, 5, and so on. That'll give me 50,000 primes. Now, from that list of primes, I want to make sure that I've got all of those broken up into lists of integers, so I better map integer digits onto all that. Okay, so now I have a list consisting of the digits of all the prime numbers. Now from that list of lists, I want to pull out the sublists that meet this pattern. So I'm going to use the command cases. So that's the second part of this exercise is we're going to do cases. We're going to take this output we produced, which we've done step by step to make sure that it satisfies everything structurally that we think it should. Because remember, step by step is better than coding all in one blob and having no idea where the errors are. Now, what condition am I going to use to select these? I'm going to use the precise condition that I built right here, the pattern match that I've already verified does what I think it's supposed to. If I do that, I end up with a list of numbers where each one of these numbers has a 2009 that occur in sequence. If I was interested in putting these things back together again into numbers, I could, from digits onto this, that'll give me a list of all of these. And then just to make sure that they're all prime, let's take this output right here. And to that output, let us apply prime q. And they're all true, which means they're all prime. And so I'm pretty satisfied that I've done this problem correctly at this point. So what have we done here? We talked about how to use substitutions and rules, what the structure of a rule is, how to apply it, and a little bit about how it comes out of the solve command and other things like that, where we don't get solutions, we get rules for manipulating variables that encode the solutions. Then we talked about how we can use rule replacements with general structures using expressions to form complicated new combinations out of existing expressions. And then we use that to begin a conversation about pattern matching, where we came up with the logic that we use to match a pattern. We talked a little bit about how we can specify the type of a variable or the structure of a variable or both in order to check to see if it's of a particular form. And then using the cases command, we can use that as a selection tool to take a long list and then break it down to a sublist that satisfies whatever the expression form that we're after is. Finally, we talked about the cases command as opposed to the select command as the tool that we use to do that selection. In particular, what we've talked about is how sequences of data are very easy to explore structurally using the extended wildcards for expressions. The single underscore, which stands for one generic expression, the double underscore, which stands for one or more generic expressions, and the triple underscore, which stands for 0 or 1 or more generic expressions, and the particular application of that to understanding sequences. So what we're going to talk about in the next lecture is going to be how we can use what we did here to build a function that has multiple definitions by looking at the input, deciding what form the input is in, and then changing the definition of the function depending on if the input has a particular form or not. And we can do that in the input using these expression matching rules that we've built out here. Okay, so I will see you guys next time. This is more abstract than what we've seen so far, but it's also the core of the more advanced programming techniques in Mathematica, actually in any language with pattern matching. So it's a very powerful skill that has applications way beyond even mathematical programming. So stick with it, do the homework exercises, read the chapters that go along with these. This is chapter 8 and chapter 9. Next time we'll talk about chapter 10, and I'll see you guys in the channel. See ya.